Swayam Prabha. Digital India. Educated India.
Welcome. In this lecture, we will study diagonalization and similarity transformation. First, we will discuss the issue of diagonalizability, which I initiated in the previous lecture, and then we will go through two very important topics in the algebraic eigenvalue problem. One is the canonical forms, and the other is the special advantages that we can take of the symmetry of a matrix. First, diagonalizability. Consider an n by n matrix which has n linearly independent eigenvectors v1 to vn with corresponding eigenvalues lambda 1 to lambda n. Some of these may be repeated for that matter, that is lambda 2 and lambda 3 can be equal, need not be all different. These are all linearly independent. Then only we will talk about n different eigenvectors. Now, if we have the matrix which has n linearly independent eigenvectors, then consider this. If we pack all these n eigenvectors into one n by n matrix with these vectors as columns, then we have this n by n matrix here, which we are denoting by S. And then we examine the product AS. Now, what will be the first column of this product? A into the first column of this matrix S, that is A V1. Since V1 is an eigenvector with eigenvalue lambda 1, so A V1 is lambda 1 V1. Similarly, the second column of the product will be A V2, which is lambda 2 V2, and so on till this. Now, we claim that the same product we would get if we multiply the matrix S from the right side with a matrix, with a diagonal matrix having the eigenvalues as the diagonal entries. Let us verify this a little carefully. What will be the first column of this product? It will be this matrix multiplied with the first column of this, that will be V1 into lambda 1, which is this, plus V2 into 0 plus V3 into 0, and so on. Thus, we find that the first column of this product is also lambda 1 V1. Similarly, the second column of this product will be V1 into 0 plus V2 into lambda 2, which is this, plus V3 into 0, and so on. That means the second column is also same. Similarly, we will find that all the columns till the nth column will be found identical to this. And this matrix, this diagonal matrix with the eigenvalues of A sitting in the diagonal positions, we will call as lambda. And then this gives us S into lambda. That means we have got AS equal to S lambda. Now, if we post multiply this equality with S inverse, then from this side S gets cancelled, here we get S lambda S inverse, that is this. That means that A can be expressed as S lambda S inverse, where lambda is the diagonal matrix with eigenvalues sitting at the diagonal locations. Similarly, if we pre-multiply both sides of this relationship with S inverse, then we get S inverse AS is equal to lambda. That means that the matrix A in the new basis S gets diagonalized, and this process of changing the basis of a linear transformation so that its new matrix representation is diagonal is called diagonalization. In this process, the transformation, the mapping gets decoupled among its coordinates. What was the necessary condition for this to happen? The necessary condition was just this, that is, the matrix has n linearly independent eigenvectors, or we can say the matrix possesses a full set of n linearly independent eigenvectors. So, this was the only requirement for this diagonalization to be possible. So, we can say this about diagonalizability of a matrix. A matrix having a complete set of n linearly independent eigenvectors is diagonalizable. That is, the n by n matrix can be diagonalized if it has a full set of n linearly independent eigenvectors. The converse is also true, that is, a diagonalizable matrix possesses a complete set of n linearly independent eigenvectors. If you want to prove this, then you will say that we already know that there exists a basis S in which the matrix representation will be diagonal, and in that case what you do? You pre-multiply with S, and then you say that we already have this relationship AS is equal to S lambda. That means this and this will turn out to be equal, and from that you can figure out that A V1 is lambda 1 V1, A V2 is equal to lambda 2 V2, which will mean that all these linearly independent vectors V1, V2, V3, V4 etc. are indeed eigenvectors. That will convince you about the existence of n linearly independent eigenvectors. So, this statement and its converse both are true. That is, if a matrix possesses a full set of n linearly independent eigenvectors, then it is diagonalizable with that same eigenvector sitting as the columns of the similarity transformation matrix, giving the new basis. On the other side, if the matrix is diagonalizable, then you can claim that it does have n linearly independent eigenvectors, a full set. Now, a few important reminders, a few important points which are actually quite simple, but they are sometimes confused. So, note these small simple statements and do not get confused. One is, all distinct eigenvalues will directly imply diagonalizability, because if all the eigenvalues are distinct, then for every eigenvalue there must be an eigenvector that is necessary for the definition of eigenvalue itself. That means an eigenvalue must have one eigenvector associated with it, if not more. So, if all eigenvalues are distinct, that means n distinct eigenvalues are there, and each eigenvalue will have associated with itself one eigenvector. So, that means n eigenvectors are guaranteed, and that implies diagonalizability. But on the other side, diagonalizability does not imply distinct eigenvalues, because it is possible that the matrix is diagonalizable even with repeated eigenvalues. In that case, a repeated eigenvalue will have that many eigenvectors associated with it as its algebraic multiplicity. So, from diagonalizability we cannot conclude distinct eigenvalues, but from distinct eigenvalues diagonalizability can be directly concluded. However, if the matrix is not diagonalizable, then from the first statement itself we will know that there is certainly some multiplicity mismatch, and for the multiplicity to have mismatch, the algebraic multiplicity must be greater than 1. So, these points we need to remember when we deal with matrices. Now, we note that diagonalizability is not possible for all matrices, and that gives rise to two questions. What simplified representation is possible for all matrices, and for what kind of matrices diagonalizability is guaranteed to be possible? The first is the issue of canonical forms, and the second is the question of symmetric matrices. These are the two important topics that we study in this lesson. First, canonical forms. There are three forms to which a matrix can be reduced or linear transformation can be expressed through change of basis. They are known as the canonical forms: Jordan canonical form, diagonal canonical form and triangular canonical form. First, the Jordan canonical form, which is always possible. A Jordan canonical form is the simplest possible form, simplest possible matrix representation of a linear transformation which is possible for all transformations, all matrices. And the form is like this, which is composed of diagonal blocks. These are blocks having small square matrices. Above these diagonal blocks and below these diagonal blocks, all the other entries of the matrix are 0. And these diagonal blocks are also specialized in their shape. Along the diagonal in such a block, say the rth block JR, we have the eigenvalues, same eigenvalue, that is one Jordan block is associated with a single eigenvalue, though for a particular eigenvalue more such blocks are possible. Now, one such Jordan block looks like this, in which along the diagonal entries the corresponding eigenvalue will be there, and just on the super diagonal there will be ones. Everything above the super diagonal and everything below the diagonal will be 0. So, this is the typical shape of a Jordan block. Such blocks sitting as diagonal blocks in this block diagonal matrix will make this Jordan canonical form. Now, unlike the previous case for diagonalization which we were studying earlier, where we looked for a suitable matrix S such that we could say this, in which this lambda is diagonal, here we will look for this J sitting in place of this lambda. So, the reduction will not be always possible to this diagonal form, but it will be possible always to this Jordan canonical form. So, the associated similarity transformation matrix S will have bunches of its columns. If J1 is 3 by 3, then the first bunch of 3 columns in the matrix S will be called S1, which will have 3 columns. Similarly, if J2 is 5 by 5, then corresponding bunch of vectors here will be denoted as S2, which will have 5 columns, and so on. So, that way if there are k Jordan blocks here, then there will be k such bunches with appropriate vectors clubbed together, and then we will have A into this entire matrix S is equal to that same matrix S multiplied with this Jordan canonical form of the matrix A, like this. Now, here if we try to see what is there in this bunch of vectors SR, then we will have a form like this, in which the number of column vectors in SR will be the same as the number of columns or rows in this square block JR. First of these entries, first of these columns will be an eigenvector of the matrix corresponding to eigenvalue lambda, and next we will have other vectors W2, W3, W4, etc., the requisite number to fill up the number of columns, which are called generalized eigenvectors. They are not eigenvectors, but they are in some sense resembling to the eigenvectors, and they are called generalized eigenvectors. Now, what are those vectors? We will find out. For that, what we do is that we consider the product ASR, that will be a bunch of columns taken from the correct location from this product. The same will be on this side SR into JR. Why? Because if on this side we will try to look for the rth block of columns, then we will have S1 multiplied with a 0 block plus S2 multiplied with another 0 block, and so on till we reach here, when we get SR multiplied with this non-zero JR block plus again SR plus 1 into 0 block, and so on. So, the non-zero component of this will be only SRJR. So, ASR will be SRJR. So, block by block, if we equate like this, then we will find ASR equal to SRJR. Then using the expression for SR from here with columns V, W2, W3, etc., we can write like this: AV, AW2, AW3, etc. in the product for ASR. On this side, SR is this and JR shape is this. That will give us V multiplied with lambda as the first column. In the second column, there will be two terms, V multiplied with 1 and W2 multiplied with lambda. So, that way if we equate column by column, then the first column equality will give us AV equal to lambda V. Second column equality will give us AW2 is equal to 1 into V plus lambda into W2, that is this. Third column will give us AW3 equal to 0 into V, 1 into W2 and lambda into W3, that is this, and so on. So, from here the first one is already familiar to us. This is from where we determined the eigenvalues. Then once eigenvector, so eigenvector we determined from this equation. Once eigenvector V is determined, the next generalized eigenvector, that is the first generalized eigenvector actually, is immediately after the eigenvector, that will be found as A minus lambda I into W2 equal to V. Once W2 is found, we can find out W3 like this from this relationship, and so on, as there are number of columns in SR. So, compared to that number, one less generalized eigenvectors will be found, because the first slot is taken by the eigenvector itself. After that, if we try to find one extra generalized eigenvector, we will find that the system of equations that come out will be inconsistent. So, that exactly that many generalized eigenvectors we will find, as many are really required to fill the block. Now, with these eigenvectors and generalized eigenvectors sitting in columns, we will have the full matrix S, which in this kind of a transformation basis change will not transform A to diagonal form in general, but it will reduce it to the Jordan canonical form, and this canonical form is always possible for all matrices, all square matrices. The second canonical form is the diagonal canonical form, which we have already seen, but now we will have another quick look at it to see what is its relation to the Jordan canonical form. In the Jordan canonical form, which is like this, if all Jordan blocks are of 1 by 1 size, then what happens? If this is not such a big matrix, but if it is a 1 by 1 matrix, that means it will be just a lambda, and there will be no place for that super diagonal 1, and that is the case of the diagonal canonical form. A few associated points we can quickly note. First is that the diagonal form is a special case of the Jordan form, with each Jordan block of 1 by 1 size. This will immediately mean that with the absence of those super diagonal ones, you have only diagonal entries in that canonical form, and that means that the matrix is diagonalizable, and that will also mean that each SR bunch will have a single vector, the eigenvector itself sitting there. So, that will mean that the similarity transformation matrix S is composed of all eigenvectors, that is n linearly independent eigenvectors as columns, and that means all linearly independent eigenvectors exist in this case when the Jordan blocks are of 1 by 1 size or the matrix is diagonalizable. And in that case, if you try to find generalized eigenvector corresponding to an eigenvector already found, then you will find that none of the eigenvectors will admit any generalized eigenvector. The corresponding equation will turn out to be inconsistent. This will also mean that for every eigenvalue, the geometric and algebraic multiplicities are same. There is a third canonical form which is of a very important practical significance, and that is the triangular canonical form. We have already come across triangular matrices in our study of systems of linear equations. Now, here when we say triangular canonical form of a matrix, then we are actually referring to the triangular form of the linear transformation. That means that we are talking about converting a given matrix to the triangular form through similarity transformations. Now, special significance of triangular form arises from the triangularization, which is always possible. What is triangularization? Triangularization of a matrix or of a linear transformation is basically the change of basis of the linear transformation in such a manner that its matrix is in the triangular form. That is, apply some suitable similarity transformation on the matrix such that the form of the resulting matrix in the new basis turns out to be like this, with all zeros here, non-zero entries only on the diagonal and above. Below that everything else is 0. This is the triangular form. Now, the practical significance of it is that this is always possible, and this is possible always through orthogonal similarity transformation. The Jordan canonical form is always possible, but for Jordan canonical form the S that you need is not necessarily orthogonal. Triangularization you can always conduct with orthogonal S, and change of basis through orthogonal transformations has a lot of practical advantage. The advantage is both analytical as well as computational. So, we find that the triangular form is always possible. In particular, if the eigenvalues are all real, then it is always possible through orthogonal similarity transformation. Even if eigenvalues are not real, even if you have complex eigenvalues for the real matrix, even then you can take recourse to complex arithmetic in your calculations, and you will be always able to triangularize the matrix with unitary similarity transformation. Whatever holds for orthogonal similarity transformation in the case of real eigenvalues, in case of complex eigenvalues, the same will be true with unitary similarity transformation. That is, S in that case will not be necessarily orthogonal, but it will be unitary, which is the complex analog of orthogonal matrices. Now, if you insist on working with real arithmetic only and orthogonal similarity transformations only, even though there are complex eigenvalues, then you can almost do the triangularization, except that for a pair of complex eigenvalues you may be left with real diagonal blocks of 2 by 2 size like this, because this is actually equivalent to the triangularized version, which is this, and you will never be able to reduce this matrix till this point unless you allow complex arithmetic in your calculations. But then with this kind of diagonal block setting, you will be able to recognize that you have a pair of complex eigenvalues there. Other than that, the rest of it you can do even if there are complex eigenvalues. Now, if you can reduce through orthogonal similarity transformation a matrix to this shape, you have not completely solved the eigenvalue problem, in the sense that you have not been able to determine the eigenvectors completely, but eigenvalues are all there along the diagonal. So, that way if you are first interested particularly in the determination of eigenvalues, then with much less amount of computation you can reduce it to triangular form and get the eigenvalues. And once eigenvalues are determined, there are some methods which help you in finding the eigenvectors with less cost. Now, other than these three canonical forms, there are two other forms which are actually not canonical forms, but which have some important advantages when we talk about computational methods for solving the eigenvalue problem. One is the tridiagonal form and the other is the Hessenberg form. These forms are advantageous in the sense that can be obtained through a predetermined number of arithmetic operations. That is, reduction to these two forms is not iterative. They can be done with a constant number of calculations. The reduction to other forms, that is Jordan canonical form or diagonal form or triangular form, they might need iterations, and there is a question of convergence. But these two forms, though not canonical forms, but they are useful, important forms of matrices to which we try to reduce the matrix through similarity transformations, and these two forms are of advantage because the reduction to a tridiagonal form or Hessenberg form can be accomplished with a predetermined number of arithmetic operations, a straightforward operation applied only once, not iterative. So, tridiagonal form, as the name suggests, has non-zero entries only along three diagonals: the main diagonal, the super diagonal, and the sub diagonal, and everything else is 0. So, this is the tridiagonal form. The reduction to this form for any matrix is, that is, for those matrices for which we apply this, is a matter of a fixed number of calculations, depends only on the size of the matrix, and there is no iteration involved, there is no question of convergence. Similar situation is there with Hessenberg form, in which other than the upper triangular matrix, one sub diagonal is extra. To this stage, reduction can be done in a fixed number of arithmetic operations, and after that, to apply further similarity transformations so as to reduce these entries to 0, that may take a lot of iterations. Okay. So, Hessenberg form is used typically for handling non-symmetric matrices. On the other hand, for symmetric matrices, we will typically try to handle it through tridiagonal forms. Next, we come to the most important topic of this lesson, and that is the topic of eigenvalue problems of symmetric matrices. Central to this issue is this very important result, and that is that a real symmetric matrix has all real eigenvalues and it is diagonalizable through an orthogonal similarity transformation. A similar result is there for complex Hermitian matrices, for which this is actually a special case. Since in our course we will be mostly concerned with real matrices, that is why in all the discussions I am trying to concentrate on the real versions of the theorems rather than going into the complex version. But the complex Hermitian matrices version is also very similar. That would read as a Hermitian matrix has all real eigenvalues and is diagonalizable through a unitary similarity transformation and no other change. The steps through which you establish that result is also similar to the one that we are going to go through right now. Now, this one sentence actually has got built into itself several smaller statements. First is, a real symmetric matrix has all real eigenvalues. That is, first issue is that eigenvalues must be all real. How do we convince ourselves of the truth of this statement? So, let us consider this itself as the independent proposition. That is, eigenvalues of a real symmetric matrix must be real. For this, what we do? We assume that there is a matrix A, n by n matrix A, which is symmetric, that is, for which A is equal to A transpose, and its eigenvalue is, one of its eigenvalues is lambda, which is h plus I k. Now, what do we need to prove? We need to prove that the eigenvalue must be real. That means this lambda must be real. So, that means its imaginary part k should be 0. That means this is the hypothesis and this is what we want to establish, what we want to show. Okay. So, fine. So, what you do? You say that since A has an eigenvalue which is lambda, that will immediately mean that lambda I minus A is singular, right? Lambda I minus A into V equal to 0, that means it has a null space in which there is a vector V and so on. So, lambda I minus A is singular. If lambda I minus A is singular, if this matrix is singular, then any other matrix multiplied to it, the product will also be singular. So, this product is also singular, that is B is singular, right. Now note what we have put here to multiply with lambda I minus a, lambda bar I minus a, because we want to establish something in terms of real quantities. We want to kill whatever complex imaginary stuff is here, and therefore we bring in the complex conjugate. Okay. Now use lambda is equal to h plus ik. So if we insert lambda equal to h plus ik here and expand this, so lambda is h plus ik, lambda bar will be h minus ik. So this gives us hi plus ik identity minus a, and here we will have lambda bar I, that means hi minus iki minus a. Now you note this, hi minus a into hi minus a, that is hi minus a whole square, ik identity and minus ik identity, that will give you minus I square small I square k square identity. I square small I square is minus 1, so that minus I square is 1, so you get only this, right. Now we found that since a has an eigenvalue lambda, so lambda a I minus a is singular, and therefore b is also singular, which is a product of this with something else. This is also singular. If b is singular, then it has a null space which has at least one vector in it, that is, if b is singular, then there must be a vector to which b multiplies and gives 0, right. So let us consider that vector as x. Some non-zero vector x will be there to which b will multiply and give us 0, and then if we pre-multiply both sides with x transpose, that also will be 0, that will be a scalar 0. So you get x transpose bx equal to 0. In this relationship, in place of b, we insert this, okay, and here at this insertion point we have used the symmetry of A. X transpose this whole thing into x. So the second part is very easy here, k square is scalar and rest is x transpose identity into x, that is this. The first one is x transpose hi minus a into hi minus a x. The second hi minus a we have left as it is, the first hi minus a we have replaced with its transpose. This is valid because a is symmetric, because identity is anyway symmetric. If a is also symmetric, then hi minus a and its transpose is same. Now note, from here to here we have hi minus a multiplied with x, and from here to here we have exactly its transpose. That means we have got this fellow's transpose multiplied with this fellow, that means the norm square, that is this part is norm square of hi minus a x, and this part is norm square of k x, right. So we have got this equal to 0. Now you see, norm is a positive quantity, norm square is certainly a positive quantity. Now you have got the summation of two positive quantities, or rather non-negative quantities, two non-negative quantities is equal to 0. Then since neither of them is like going to be negative, so for the sum to be 0, each of them must be individually 0, and that means x is a non-zero vector, so k must be 0, and we come to the conclusion of our proof. K is 0, which will mean that lambda is h. So what does that show? That shows that only due to the symmetry of the matrix which has been used at this step, we come to the conclusion that k must be 0. That means lambda is real. Now the first point of the proof is established. Other than this real eigenvalue issue, what else is there in this statement? In this statement, it is that the matrix is diagonalizable. That means it has a full set of n eigenvectors. A complete set of eigenvectors exists for a symmetric matrix. We consider this statement separately. A symmetric matrix possesses a complete set of eigenvectors. For that, what we do is that we consider a repeated real eigenvalue lambda of A, because if all eigenvalues are distinct, then we already know that each distinct eigenvalue will be associated with at least one eigenvector, which will immediately tell us that n eigenvalues will give n distinct eigenvectors. So there is nothing to examine there. So what we do is that we consider a repeated eigenvalue which might create some trouble. So we consider a repeated real eigenvalue of the matrix and examine its Jordan blocks. What we want to establish? We want to establish that all Jordan blocks will be of 1 by 1 size. There will be no place to write that super diagonal 1. So if all Jordan blocks are of 1 by 1 size, then the result will be a diagonal matrix. So this is what we want to establish, right? So what we do is that corresponding to that eigenvalue lambda, suppose eigenvector is v, then we will have AV equal to lambda v, and we try to find out, we try to determine the first generalized eigenvector w, which must satisfy this relationship. Now if it has to satisfy this relationship, then by pre-multiplying both sides of this relationship with V transpose, that is by taking dot product or inner product of this with V, we will get V transpose, this whole thing is equal to V transpose V. Now we open this V transpose A W. Here in place of A, let us write A transpose. That is valid because A is symmetric. This is the place where we are utilizing the symmetry of the matrix. V transpose A W has been written as V transpose A transpose W minus lambda V transpose identity W. So lambda V transpose W, that is equal to this. Now the right side V transpose V is norm V square, that is obvious. Here V transpose A transpose is the transpose of AV. So we have got AV transpose W, and here it is taken as it is. But then since V is eigenvector corresponding to lambda eigenvalue, that will mean that AV is the same as lambda V. Then what is this? This is lambda V transpose W minus lambda V transpose W, which is 0, and that means V norm square is 0. What does that mean? That means V is a 0 vector, but that cannot be the case, because V is the eigenvector for which linear independence is a must to qualify as eigenvector. So in which direction is the only information. So you cannot have an eigenvector which is 0. So this is absurd. That means it is not only absurd, it basically means that this gives rise to an inconsistency. That means there will be no W, no generalized eigenvector which will satisfy this. That means that the eigenvector will not admit any generalized eigenvector. That will mean that all Jordan blocks are of 1 by 1 size, which means that it is diagonalizable. So we have established 2 points from this complex statement. A real symmetric matrix has all real eigenvalues and it is diagonalizable. But till now the matrix S related to the diagonalization, the similarly transformable matrix can be anything. The further statement says that it is diagonalizable through an orthogonal similarity transformation. That is, in the diagonalization process, we can use a matrix S which is orthogonal. That means the matrix S which houses the eigenvectors should have all mutually orthogonal columns. Do eigenvectors have to be mutually orthogonal? We say that in 2 parts. First, we say that eigenvectors corresponding to distinct eigenvalues are necessarily orthogonal. So here the proposition is that eigenvectors of a symmetric matrix corresponding to distinct eigenvalues, unequal eigenvalues, are always orthogonal. They must be orthogonal. To show this, we take 2 eigenpairs, 2 eigenvalues lambda 1, lambda 2, and their corresponding eigenvectors v1 and v2, with the statement that lambda 1 and lambda 2 are not equal, and we want to show that v1 and v2 are orthogonal. They must be orthogonal. So for that, we take a very simple means to establish this. We evaluate v1 transpose a v2 in two different ways. In the first case, we simply take AV2 as lambda 2 V2, because lambda 2 and V2 are the eigenvalue eigenvector pair. Okay. So, in place of AV2 we write lambda 2 V2, lambda 2 being a scalar comes out and we get lambda 2 into V1 transpose V2, right. In the second case, in place of A we use A transpose, that is the place where we use symmetry, and in that case V1 transpose A transpose is the transpose of AV1, but AV1 from here is lambda 1 into V1, and that will tell us that this turns out to be lambda 1 into V1 transpose V2. Now note that the same expression evaluated in two different ways without utilizing symmetry and utilizing symmetry gives us two different expressions, right. So, we subtract. On this side subtraction will give us 0, on this side what it will give? It will give lambda 1 minus lambda 2 V1 transpose V2, that is 0. We have already taken the assumption that lambda 1 and lambda 2 are not equal, that means this factor cannot be 0. So, only way this can happen is that this factor must be 0, that means V1 and V2 are necessarily orthogonal. So, this is the case for distinct eigenvalues. What will be the situation for equal eigenvalues? That is an eigenvalue appearing twice giving us two eigenvectors. Do they also have to be necessarily orthogonal? Not necessary. But then see this, what we want to see here, we want to establish that corresponding to a repeated eigenvalue of a symmetric matrix, an appropriate number of orthogonal eigenvectors can be selected. What is the idea behind it? If lambda 1 and lambda 2 are same, unlike this case, then the entire subspace V1 and V2 is an eigenspace. So, if there are two vectors which are eigenvectors corresponding to the same eigenvalue, then it is not necessary that they are orthogonal, but then the entire plane formed by them is an eigenspace. That means any vector in that plane is an eigenvector. So, if in a plane we have infinite possible eigenvectors available, then two mutually orthogonal eigenvectors we can always pick up. So, that means we can select any two mutually orthogonal eigenvectors for using in the basis, that is for filling up the appropriate columns of this matrix S. That is, corresponding to repeated eigenvalues, orthogonal eigenvectors are available. The eigenvectors that we pick up do not have to be orthogonal, but if we want we can always get orthogonal eigenvectors. So, that is why it says is diagonalizable through an orthogonal similarity transformation, that is it is possible to work out an orthogonal similarity transformation matrix with which we can diagonalize the matrix, the symmetric matrix. Further, what do we get? So, you see that in all cases of a symmetric matrix we can form an orthogonal matrix V such that in place of V inverse, in this case we were writing S inverse. Now, since we are talking about orthogonal matrix V in place of S, so for orthogonal matrix V inverse is same as V transpose, which is a lot easier. V transpose AV is lambda, which is a real diagonal matrix. Further, try to pre-multiply this equation with V and post-multiply with V transpose, then you get this. The matrix A can be represented in this manner, V lambda V transpose, where V is an orthogonal matrix and lambda is the diagonal form of A. That diagonal form is always possible, and that is always possible through an orthogonal similarity transformation V. This gives us a lot of facilities, and this is greatly helpful because symmetric matrices appear in many locations in the analysis in applied science and engineering, and it helps that so nice properties, so interesting and useful properties of symmetric matrices are there, and symmetric matrices appear in most of the applications again and again. So, most of our problems are comparatively easy, and the enormous amount of facilities that this representation gives us is here. First of all, this expression A equal to V lambda V transpose can be written in expanded form like this. If you try to multiply these three matrices and open it in the form of an expression, you will find that you get lambda 1 V1 V1 transpose, because you see, if you first multiply these two, then you will get what? You will get lambda 1 into V1 transpose plus 0 into this plus 0 into that, and so on. So, here in rows you will find lambda 1 V1 transpose, lambda 2 V2 transpose, lambda 3 V3 transpose, and so on, with which when you multiply this, then you will get V1 into lambda 1 V1 transpose plus V2 into lambda 2 V2 transpose, and so on. So, finally, you will get this summation lambda 1 V1 transpose, V1 V1 transpose plus lambda 2 V2 V2 transpose, and so on. You can express it like this, right. This gives rise to a further lot of possibilities. One is that if a particular matrix, huge matrix, 4000 by 4000 matrix, has eigenvalues which are organized in descending values, descending absolute values, the first 10 are large, and compared to them the next ones are extremely small. Then what you can do for that, for the storage of that 4000 by 4000 matrix, you can simply store the first 10 eigenvalues lambda 1 to lambda 10 and throw away lambda 11 to lambda 4000, and the corresponding first 10 eigenvectors you stored, other eigenvectors also you can throw away. Later, when you need to reconstruct the matrix, these 10 eigenvectors with their corresponding eigenvalues will be able to reconstruct the matrix completely by a summation of not 4000 items like this, but just 10, because the contribution of the rest of them will be extremely small. This is one advantage. Efficient storage with only large eigenvalues and corresponding eigenvectors. Rest of the things you do not have to store. In deflation technique, we have already seen the application of this expression. That is, if the, and this works only for symmetric matrix. If the matrix is symmetric, then there is a representation like this, and after we have determined V1, then from A, if we subtract this, then what remains has the same eigenstructure as A, except that its eigenvalue corresponding to eigenvector V1 turns out to be 0 rather than lambda 1. The rest of the eigenvalues and eigenvectors are unchanged. That is the deflection technique, which helps us in finding a few top eigenvectors, a few top eigenvalues and corresponding eigenvectors. Apart from that, the orthogonal diagonalizability of the matrix in the case of symmetric matrices helps us in working out practical algorithms which are stable, in which the numerical errors do not grow very fast as iterations proceed. Therefore, whenever there is a choice between applying a general similarity transformation and applying an orthogonal similarity transformation computationally, we always prefer to apply orthogonal similarity transformation. And in the case of symmetric matrices, orthogonal similarity transformations alone suffice to reduce the matrix completely to diagonal form. In the case of non-symmetric matrices, first of all, diagonalizability is not always guaranteed. Even when the matrix is diagonalizable, reduction to diagonal form is not always possible through orthogonal similarity transformations. In fact, that is not possible. So, you have to take the help of similarity transformations which are not orthogonal in the case of non-symmetric matrices. In the case of symmetric matrices, you can conduct the entire operation with only orthogonal similarity transformation. This is why solution of symmetric matrices eigenvalue problem is a lot easier compared to general non-symmetric ones. Now, the complete picture of different forms, some the raw form and some the final desired form that we have, we can see here, and any block here in this schematic diagram which is on the right or which is below is typically easier to handle for the eigenvalue problem compared to corresponding other blocks which are on the left or above. So, in that understanding we find that compared to a general matrix, all other matrices, general means which may be non-symmetric, all other forms are easier to handle, and the diagonal matrix is the one in which the eigenvalue problem is actually already solved, right. So, that means if we have a matrix in on one of these forms on this side, then any algorithm, any part algorithm which helps us to move from this end to the right side or below southeast side, then that is one contribution to the solution of the algebraic eigenvalue problem. That is, from the general matrix we might try to reduce it to either the Hessenberg form or the symmetric form. If we have a symmetric matrix, then we try to reduce it to symmetric tridiagonal form. If we have it already in Hessenberg form, then we try to reduce it to tridiagonal form, which is comparatively easier, or we will try to reduce it to triangular form, which is more often the case. From triangular or tridiagonal or symmetric tridiagonal, another round of reduction will take us to diagonal form if a diagonal form exists for that matrix, right. In this case it will certainly exist, and any movement along the arrows will mean that we have accomplished one more stage in the solution process of this eigenvalue problem, and all these steps, all these reductions must be carried through similarity transformations only. That is, we must multiply the matrix A on the right side with one matrix and with the left side with its inverse, then only it is a similarity transformation, and that will mean that it is basically the expression of the same linear transformation in a new basis, the basis S. So, through similarity transformation only we must do all these transformations. Straightforward reduction like Gaussian elimination only from one side will damage the eigenstructure. So, the similarity transformations should be applied like this, and through this any step is preferable if it helps in the direction like this or like this or any way like this. So, the question arises, how to find suitable similarity transformations which help us in moving from this direction to this direction in general, that is reduction of the problem. How to find suitable similarity transformations? There are four standard ways of working out suitable similarity transformations. They are based on rotation, reflection, matrix decomposition or factorization, and element transformations. These four methods of finding suitable similarity transformations we will study in the coming lectures or coming lessons. For the time being, to summarize the important issues that we have seen in this discussion is that generally possible reduction, which is possible for all matrices, is up to Jordan canonical form. Condition of diagonalizability and the diagonal form we have studied, and we have studied the form which is triangular form, which is possible with orthogonal similarity transformation. Note here that in the previous chapter in the book there is an exercise which gives you the steps necessary to show this important result, to establish this important result, that any square matrix can be reduced to a triangular form with only orthogonal similarity transformations. This is an important result, and I will strongly advise that this particular exercise, which gives you the steps to establish this important result, you must go through. Okay. The other useful non-canonical forms are tridiagonal and Hessenberg forms that we have come across briefly, and the most important lesson of this particular chapter, of this particular lecture, is that orthogonal diagonalization of symmetric matrices is always possible, and all these reductions must be carried through similarity transformations only. So, I would also advise you to go through some of the exercises of this chapter before proceeding further to the next lecture. Thank you.